Thank you. So hey everyone, my name is Robert, and I will be doing talk about using your favorite programming language in React Native. And the talk actually is about our project that is related to that called PolyGen. So more on that later. Quickly, it's an alternative to a TurboModules approach, but yeah, we'll go into that soon. My name is Robert. I'm a senior software engineer here at Callstack, currently working in incubator team. I'm a React Native core contributor and open source contributor in my free time. Let's go to the core of the presentation. Let's talk about React Native. So we all love it, I assume, for the good reasons. It allows us to create mobile apps with the web technology we all know, without all the hassle of native applications and native technologies. But there are some barriers when you want to go deeper or extend it further than what we are given. For example, what if I would like to create or extend my applications using programming languages such as Rust or maybe Go? Then unfortunately, you're having a very hard time, and I can sum it up with this GIF here. It's not very easy, unfortunately, not yet, at least. And you're left with C++ and the native embedded languages. So going back to React Native, it started from React for Web. So we have this one platform here. We have support in React Native for the Apple platforms. So all the known stuff like iOS, tvOS, macOS, visionOS, iPadOS, and watchOS. There's no support for watchOS. Yeah. So there is that, the Apple platform, the Apple ecosystem, and Android ecosystem, written as an aggregate Android here, but it includes TV as well, and any other out of 3 platform here really. So let's focus on the native part. So let's group all the native platforms in one column and talk about in greater detail. React lives in JS world. It's written in JS, as we all know. You write UI using JS, and there's this another world of native UI, so native components, which are completely separate. So there needs to be something that connects those two. And in the old architecture, there was something called JS Bridge, which is like a client-server approach, where the communication was asynchronous. All the messages needed to be serializable, so you couldn't pass around some native data. It was suboptimal in performance as well, so we migrated off into a different approach. But it was a good start. So we don't have it anymore. Right now we use something called JSI, which is JavaScript interface. It's new architecture, and it's much more faster, it's more powerful, and we actually can pass around native data. We don't need to serialize all the data between those two contexts. So let's quickly go deep into the JSI. So what is it really? It's written in C++. It's an abstraction over multiple JS engines, such as JC of Safari and Hermes, written specifically for React Native from Meta. It allows us for direct access to JavaScript virtual machines, so there is no serialization involved. You can expose functions and objects directly, and you have access to the event loop, which is gives us a lot of opportunities. And we also use CodeGen to simplify the complex type conversion. So you can pass an object from JavaScript to C++, and the resulting object is an instance of a struct. So it's all typed and safe. Pretty cool. And here's an example of what JSI really looks like. So we have a runtime that contains our JavaScript world. We can access a global using a specific function. We can access add function from this global object. We can call it using 2 arguments, as shown in the last line, and get the result using a method. Obviously, because this is a snippet of C++, It probably does not compile, it's just for preview purposes. JavaScript is loosely typed, so the add function can return a string for some reason, so this probably would throw an exception, but we assume the function returns a number. So this is a simple example of what a JSI looks like. So to visualize all this, we have our React realm here that contains all our JavaScript code. And we have a second realm, native realm, which contains Android or iOS functionalities here. So in the React realm, we assume that we are working on a TurboModule. So like we want to extend React Native app with some additional logic. So we have our TurboModule, and the communication between React and our module is using JSI. So this React realm we can think as that C++ code, and we need to communicate with native realm, which is in different technologies. So how do they communicate? How we can combine those two different realms? The answer is C or C++ ABI. Don't worry, this idiom can be really hard, but it's not really that hard, don't worry. It's just a way to communicate with different languages using the lowest known denominator. In this case, it's like probably C API. And let's look at it from different perspective. We are not combining React Native with native platforms. We are essentially combining C++ with Java for Android or Objective-C or Swift in Apple ecosystems. So this is like a different tackle on this issue. So whenever you want to use or combine those two realms, you're looking at this issue specifically about combining those two languages. So for Android, it's JVM, be it Java or Kotlin, and for Apple, it's Objective-C or Swift, which are both compiled. And for any other out of three platforms, probably for Windows, it's like C++ with some other extensions. So the mileage can vary. And as you can see, there are a lot of systems here and tools that need to be working and combined for all it to work, which is probably problematic. And let's not forget that with this, you cannot build an app. You need a build system. So let's also add some build systems here to make it all work together. So for C++, you're using CMake. CMake is also used in Android with Gradle, and for Apple, it's Cocopos with Xcode. Xcode, it's a lot of tools here that need to play together to make it all work, which is subpar and not really wanted here. There are some challenges here that I want to outline. We usually have to build from source, which make our build system integration a bit harder. There are no binary artifacts we can use. So if I want to use a library, I need to embed it, build it from source, rather than use the already available binary artifact. And we cannot distribute it easily. So we need to integrate those different build systems, which is not easy and is very troublesome. We also need to tackle the issue of supporting multiple languages, as mentioned, and also different architectures and platforms and systems. So there are like ARM64 for phones, x86 for PCs. So there is a lot to handle here. And obviously, we need to cross language boundaries because that's the core issue here. So like C or C++ interop between different languages using C ABI or C++ ABI. And that's a lot. We don't want to handle all those issues. We chose React Native because it's simple. We like React. We want to create native apps. So that's complicated, and that's too hard. So in native world, when you build an application, you build an application for a specific platform. So for example, if I want to build an app for iPhone on my laptop, I need to specify a target that the application will run on. So if I do not specify, yet it assumes that the app will run on my laptop, which is not the case. So here is like a simple example using Clang, which is a compiler for C++, to specify that my library or application will be run on this magic triplet. The like target is the notion for iPhone platform. We also need to build for Android phones, so that's the same architecture but different system and platform. We also may want to build an app for macOS using Apple Silicon, or maybe using macOS with Intel CPUs, so that's another target. And maybe we want to build a desktop app for Windows PCs, which is another target, so that's a lot. And the same problem goes when you want to use Swift, Rust, or whatever else. Any compiled languages need to have a target specified. So for every platform you support, you need to do this one way or another, either manually or through build system. But what if we could simplify this? What if there was something that exists already that solves most, if not all, of the issues, and leaves us with the real issue of business logic and not with the technological tools here? What if I could instead specify a single target that builds for every platform available, and that is supported by almost all compilers and is a standard? What if I told you that this standard already exists and is WebAssembly? So we can use WebAssembly to target almost any platform, mostly. So it solves the issue I already mentioned of having multiple targets and maintaining all of them. So let's do a very quick recap on what WebAssembly is, at least in this context. So it's a low-level bytecode and virtual machine, so therefore it's rather fast. It's platform agnostic, so think about assembly language that runs everywhere. So we don't need to worry about CPU architecture or a platform or whatever. It's isolated from the system, so the modules from WebAssembly do not see anything that we do not provide them. So there is no issue between different system APIs because there is none. You need to provide it manually. And because there's a single standard, if you match it, it works everywhere. Yeah, so that solves the issue of different operating systems, for example. And the most important aspect, at least in the context of this presentation, is that it has an unified ABI. If you remember previously, I mentioned that the communication between those two realms is done using C or C++ ABI, which is complicated to use in different languages. But using WebAssembly, we have a unified ABI, so any language that compiles to WebAssembly can call another language that compiles WebAssembly. So, for example, if we compile a code, a piece of code, for example, in Rust, into WebAssembly, we get a WebAssembly module. Modules can have two formats, either binary or textual. That's not really relevant here. What is important is that each module has a explicitly and well-defined, specified contract that is set of imports. So anything that it requires, we need to provide to it, and as a well-specified set of exports. So think of a WebAssembly as a glorified calculator. It cannot do anything you do not provide it. So if you wanted to access network, you need to provide those functions into the module. And each module can be instantiated multiple times. For example, each module can run on a different thread, can be provided a different set of imports. So one module can be like a class, and we can have multiple instances of such module with different arguments, parameters, and all other dependencies. So for example, here we have a simple WebAssembly textual module. Let's not go into much detail. It's written in like a Lisp-like format. There is a function that is imported, and what we can see here, there is no body of this function. So it's a kind of a contract that says that this module needs a function called add from host namespace that accepts two numbers and returns a number. And we have another function that is exported called add5, which actually adds 5 to a number you specify. And there is a body of this function, and that's it. Nothing external is happening here. It's a well-defined contract on what goes in and what goes out. And using the module in JavaScript looks more or less like this. This is an example from MDN on using WebAssembly. So here we are using WebAssembly namespace and compile streaming function. So we fetch the module, wait for it to be compiled. Then we need to specify the set of imports. So as I already mentioned, each of the module has well-specified imports. And here we need to provide those to the module for it to be run. So what we provide here is the add function that essentially adds two arguments here. Then we initiate the module using the imports provided. So as I mentioned, you can create an instance using different imports. And then we call the function using instance.exports. This is how it's done in web, and it's well-defined, it's standardized, it's widely used already. So the benefits here is that it's easy to target from multiple compilers. Many of the compilers already support WebAssembly, and there is no need to tailor the build systems. It all works out of the box. It works on web. So imagine creating a TurboModule that also works on web. So you don't need to worry about having the same code written once for web and second time for React Native. It's really fast. Essentially, it's just a very low-level bytecode, so it's very, very fast, and it's still getting faster every release, every standard, actually. It's language and platform agnostic, so we can only focus on the logic, and any low-level aspect like platform or CPU architecture is abstracted away. It's meant to be run in browsers, so we just focus on the code here. So where does this leads us in context of React Native? I would like to introduce you to our new project called PolyGen, which is still in active development, just a quick note. So what does it do? It's a toolkit for embedding React Native, embedding WebAssembly in React Native. It provides web API compatibility. So if you have a web app that already uses WebAssembly and it's using web API for doing so, which it probably does because that's the only way you can use WebAssembly, it works in React Native, works out of the box. It provides near-native performance. Our goal is to make it actually really, really near-native performance, and more on that just a second, on how do we achieve this. So let's imagine we have a piece of code, a native module we want to write in, for example, Go, and the second one we want to write in Rust. So what we can do, we compile each module using the native compiler for each language into WebAssembly module. What happens next depends on the platform. In case of browser, we need a JavaScript piece of code that loads those modules from the network, waits for them to be fetched, compile on the browser, and run on the browser. So there is a slight delay, but the execution time is close to native because it's compiled in the browser. So how does it compare to PolyGen? We use a pretty different approach here for maximizing the performance. So we do not care about WebAssembly as a virtual machine really here. We are actually leveraging its unified ABI and unified build system. So what we do with each WebAssembly module is that when using PolyGen, we compile each module back to C. And this C code is becoming part of your application, just as you would write this code by hand in C or C++. This gives us the best performance we can achieve. And then, because it is using C and C++, the communication with the React realm, using JSI, is very simple and has almost zero overhead. So it's like writing the code essentially just in C. And we do not need to cross any language boundaries here. We are still working in C++ realm, so there is no serialization or external function calls. There is no interpretation, so it's super fast, and there is no just-in-time compilation, so it can be used on Apple devices, which forbid just-in-time compilations. So if you remember the slide that I showed you a moment before, this is an example of using WebAssembly on the web. This already works using PolyGen. So you can use this right now in your React Native apps. As you can see, as I mentioned, we're using fetch to download the module, but as you may guess, we do not really fetch this module. All of the code, all WebAssembly code is pre-compiled into the application beforehand. So what we are doing here is we are fetching the module and finding its signature to match the corresponding native code. This is suboptimal, but it works just to match the web API. We have a better approach, that is to integrate with the bundler. So you can only simply import your WebAssembly module, create an instance of it, and it works. You don't really import the module here, you just import a reference to it, so we know which module to create. There are some limitations with this approach currently. You cannot dynamically load modules because each module needs to be predefined during compilation for best performance, so you cannot load arbitrary code and evaluate it without interpreter or just-in-time compiler. So there is one limitation, but we see it actually as a security benefit because you cannot run untrusted code this way. Compiled modules become part of the application, which is super fast. WebAssembly standard is still pretty limited. We are working on integrating all the current standard, but the standard itself does not cover all the needs of the different languages. But WebAssembly is growing very rapidly, and the standard is getting better every year. There are no workers in React Native, so there's no threading yet. We are working on it as well. Not all extensions and features are supported yet. But this is a temporary limitation because the library is still in development. So to recap what the PolyGen is. Can you write both web and native? Yes. Is it high performance? Yes, it is. Is it easy to use? Yes. Can you write Rust, Go, or even COBOL? Yes. You can actually. Cloudflare did a COBOL to WebAssembly, which you can use in React Native if you really want. And a quick example that already works. I was working on an app that needed to do a digest from using crypto library, which is not available in React Native. So what I did is this is a simple snippet from Rust code that actually computes the snippet using a specific algorithm. I used WebAssembly to create a WebAssembly module and export this function. Here's a very long snippet, but this is a whole view from my example application. So this is available on a repo where you can open a screen and compute this digest using WebAssembly module. And it works. You can actually call Rust, Go, or whatever you want to write your business logic today. And yeah, that's it.